So welcome everyone to the Warren Lecture. It's my pleasure today to introduce Professor Igor, I need to get the Vusanovic.
Yes.
I think I did that correctly, Mickey, I
yes.
hope, right?
Yeah,
well, I tried. I've been practicing.
Almost.
I just know him as Igor. And Igor's going to give the seminar that I always wanted to give, I think, in this department. He's going to go through methodically talking about how you model solidification processes, which is something which is very dear to my heart, and hopefully by the end of it, it'll be dear to some of your hearts. So looking at all the different processes and computational procedures that you need to use to be able to model phase change processes. So Igor got his bachelor's degree in the University of Belgrade, which I think a number of people in our department have connections to. And then he got his PhD in the University of Montenegro, but a kind of joint program PhD between Montenegro and Purdue. And they were all in mechanical engineering. Of course, Purdue has a very famous heat transfer mechanical engineering department. And I first met Igor 10 years ago, and the first thing he told me was that he'd been sleeping with my papers. He said that when he was a student, he had my papers under his pillow and he read them every night. And that kind of got my attention. But so then since then, we've been kind of very good friends and colleagues and worked on a number of interesting problems. And I think Igor will touch on some of those as he goes through. The other thing you should know about Igor is he has something very close and similar to a former faculty member of ours, Effie Fafula, and that he didn't really want to be an academic. His real kind of reason to live and what he really would like to have been was a Formula One racing driver. Yes. That's why he went into mechanical engineering. I told him not to race through this too fast.
Yes.
But Igor, the stage is yours.
Okay. Thank you, Juan, for nice words. Ladies and gentlemen, dear colleagues, it's a great pleasure for me to be here today and to give a talk about what we are doing recently. And it's really true that I had a paper for Prakash Waller from 1987, so when I was a master's student, and then I get interested for the phase change phenomena. So since today, I'm still using, and still there is a lot of challenges that we have to find out in this field. So besides I'm a professor at my university, I'm a dean of mechanical engineering. It's like a head of the department comparing to the US university. So I also have a desire to extend the collaboration, and maybe then I have a chance to talk with some chief of the department about ideas that I have. So looking forward to see that in the recent future we will have some other opportunity to visit us or to exchange the students and professors. Probably you ask yourself, where is that goddamn Montenegro? And I will tell you this, in Europe, if you look at the Mediterranean, we are a small spot on the Adriatic coast, and we were part and past of former Yugoslavia. And you probably heard about it, the country which has disappeared in the 90s in a bloody civil war. We are the country, we have a residents less than 1 million, but we are still bigger than Luxembourg, for instance. And at least, or San Marino, or whatever. And we are independent. We are recognized since 2006, but we are very proud that we stand alone for almost 1,000 years, and especially conquered with the Turks during the dark age of mid-century, because the Ottoman Empire was a cover whole Balkan. And yeah, but we are recognized officially, let's say, in the 19th century, 1876, and recently in 2006. We have a Mediterranean climate, we have a multinational and multi-confessional culture that we are very proud. So if you look at the country outside of US, which is multicultural, multi-confessional, it's my country, and we are very proud in that. We survived the civil war without any kind of injuries, and yeah, we are only one republic in former Yugoslavia without any kind of conflicts. So we have a relation with the US since 19th century, but yeah, now I will tell you something more. First of all, I'd like to show you some incredible pictures. we are the country with the high gradients, I can say. If someone asks me what kind of country we are, we are a country with the high gradients. So gradients is something that we are often using in our research. We have a beautiful coast. We have a 220 kilometers of coast. On the north, which is only about 100 kilometers from the coast, we have a second deepest canyon in the world. Only Grand Canyon here is bigger than this. We have very famous places for celebrities like St. Stephen, place known as honeymoon places of Prince Charles and Princess Diana. Maybe it's not so happy if you try, if you get married and to go there. I don't know. So we have beautiful mountains, and some people says that some of my friends from Switzerland, they call us Balkanian Switzerland. So this is some facts.
Is that like San Antonio?
San Antonio.
Texas?
San Antonio, Texas?
They call it the Venice of...
Venice.
the Venice of
Oh, we have our Venice. I will show you the picture of our Venice. So this is some facts and figures. I will not spend the time too much. You can Google it more. Now Google is, I mean, you know, you can see everything. So I'd like to emphasize that we have different activities in the country. Most intensive activities is tourism, but beside that we have agriculture. We are producing wines. We have a biggest winery yard in Europe. If you decompose that winery yard, which is near the airport, it's like from my country to Moscow, in one line, one country to Moscow. So it's the biggest one in one piece. Regarding the industry, we have a steel making and aluminum industry. We have a lot of deposits of bauxite. So we will see what's going to happen in recent future. Is he going to be developed more or less, depending on what they will decide to do that with the resources. Our major trading partners are Serbia, Croatia, and Bosnia, our closest neighbors. And we are very close to Greece and Hungary. And since July this year, we became a member of NATO. And that means for the Slavic country that this is step number one to join the EU. So I expect to, in the next, let's say, maybe 5 or 10 years, to be a member of EU. So this is some short information. And now I would like to go through the outline and what we are to talk today. First of all, I'd like to give some acknowledgement to the phase change phenomena, and then go through the basic equations and approaches. And then I will introduce more complicated things like fluid flow equations, and then how we treat the Maschwitz region. And Van Wolle is one of the legend of that in that field. And then we'll go through the multi-component system to see what's going on when you have a not pure substance, and what is the key phenomena and key defect that shows, which is very undesirable in the metal industry. We call it macro-segregation. And then after that, I will show you some results that we published recently regarding the modeling, where we find out that verification and green convergence, it's still open problem in solidification models. And then I will close with the latest achievement. I mean, this is just the first steps, and maybe to get some idea how to treat the solid movement. When you say phase change phenomena, it's around us everywhere. It's one of the most important phenomena in the nature. You can see it when you look at the vaporization of the water. This is a liquid vapor phase change. And you can see it in the most dangerous way as a solid liquid phase change that occurs in nature, especially on the poles, which threatens to our civilization. And regarding the technical activities, the most important phenomena is in metal industry, when we have a casting of alloys, steels, aluminum alloys, and so on. Also, because I'm aware that I'm at the Department of Civil Engineering, I asked myself, is there some phase change in this field? And I spoke with Van, can you show me some example about that? And he proposed me to put the disappearing of delta or forming a delta. And it's a quite, we are using quite a similar or same equations. So we can say that this is one example of phase change too. So we believe that our approach can be easily switched to the different systems and for different purposes. Talking about phase change without mentioning a Stefan, it's not a real world, because, and I'd like to emphasize who was Josef Stefan. He was a Slovenian physician and a poet who lives in Austro-Hungarian Empire in the 19th century. And we are in time of Yugoslavia, we were very proud of him because he established some very fundamental law of physics, like like radiation law, Stefan Boltzmann constant. His first associate was Ludwig Boltzmann, professor at the University of Vienna, and they have statues there. And in time of Yugoslavia, we were very proud of him. And in Slovenia, which is capital, in Ljubljana, which is capital of Slovenia, there is a huge institute named Josef Stefan. Among many things, he defined a problem that in literature is known as a Stefan problem. So the Stefan problem purely is a problem when you need to solve two equations, one for one phase and another one for another phase. Those equations are the same, as you can see. The only difference is a physical property of phases, and the equation is a pure diffusion equation, and you need to solve the temperature field. So maybe some numerical guy here says, what's the problem here? Because it looks very simple. It's not so big problem. But this phase change interface changes through the time because of the something that occurs on the border between the solid and liquid phase, or solid, or liquid or vapor, whatever you like to do. So what controls that movement of the solid-liquid interface is this equation. And this is a solid-liquid energy balance equation. And we can roughly say that energy that leaving the interface through the solid minus energy arriving to the interface from liquid is something which controls the movement of the solid-liquid interface. So LV is a velocity of this solid-liquid interface, and L is a latent heat, because the only differences between the side, beside the temperature from left and right side, is latent heat. Latent heat is something which is not visible, cannot be sensed, and liquid has it, solid doesn't have it. Doesn't has it. So numerical guy says, if you want to solve those two equations, you have to use some numerical technique, whatever you want. Finite difference, finite element, control volume, etc., etc. So you need to have a mesh on the left side and on the right side of the domain. And in the meanwhile, because this mesh is not constant, because phase change interface is moving, because of that, you have to calculate and remesh, do the remeshing all the time. So when you look at it from the one perspective, it's a very easy, it's very simple equations, but the problem is how to do remeshing. You have a guys now, and because of this, we are in 21st century. When I was a student and when I read the papers, that was a huge problem. Now I'm sure that there are many guys who can solve this very efficiently. But old-fashioned guys, as I am, probably, and one, like to have an alternative. Is there an alternative to this? To do not solve two separate sets of equations? Yes, there is, of course. Why am I asking if there isn't? So the problem is, if we introduce the new parameter, which we called liquid fraction, we see that from the right side of the boundary, we have a liquid. It's almost liquid. Everything is liquid. Yeah. On the left side, everything is solid. And we say liquid fraction equal 1 on the right, and liquid fraction is equal 0 on the left. And we have a sharp interface. We have a sudden jump. So this is a problem. How we can go through? We can say, okay, we will introduce something which is not so sharp, So to smear the interface, to allow smooth change, to do not jump suddenly like is on this picture. How we can do that? We can introduce we call it diffusive interface. Diffusive interface is a trick how to overcome the problem. Instead of sudden jump, now we can establish some function and say that we are traveling from the solid to the liquid through this smooth line. And you can choose, as you can imagine, for this smooth line, some different function, let's say linear, or some quadratic, or some interpolation, or whatever. And also you can choose the whatever you like, what is the width of this zone. And this width is, I'd like to also notice that in pure substances, phase change is a process where the temperature is not changing. It's a constant. And then we are artificially introduced this small region, Tm minus epsilon and Tm plus epsilon, and we say, okay, this is very small, but temperature solidification occurs in this small region. So now we made the basis to establish the one single equations instead of two, and to solve the problem of solidification. What is that equation? We know that in literature as an enthalpy equation, instead of dealing with the temperature separately on the left and right side, we can go with only one equation. And this one equation fits both sides of the domain. So what is the H? H is an enthalpy, and enthalpy is at C times T. We assume that C is equal between liquid and solid, but it's not. But we wanted to first start from the very simple models just to understand phenomena and then introduce more complex details later. HL is a CT plus L. L is a latent heat. And in this zone, in this diffusive zone, H is a combination between solid and liquid. And if you combine those two, HS and HL, you will get this simple equation, C times T plus G, which is function of T or delta times L. Now, solving this equation, we can go through, we can satisfy both domains. And the key question is how we will know where is the solid-liquid interface. If you know the position solid-liquid interface, this is something that was a huge problem in two-phase modeling, and now we have to know where is the solid-liquid interface. So, solid-liquid interface is always in the control volumes, where the G is between 0 and 1. So we need to have some additional equations to calculate G, and we can say, okay, anywhere where G is between 0 and 1, this is a position that solid-liquid interface must go through. You see? And tracing that control volumes, just tracing that control volumes, we can see where is the solid-liquid interface. So, and instead of solving the complicated equation that I show you of heat balance between solid and liquid, now we have a very simple solution to see where is the solid-liquid interface. So, if we know how G look like, and if we calculate the G in every control volume, we know where is the solid-liquid interface. Okay. That was a problem where we don't have a flow. What happens when we introduce the flow in liquid phase? Because the phase change always occurs because that liquid is not steady. It's always circulating because of something, you know? Even in the ocean, when you put even in a cup, when you put the piece of ice in the cup, you can see under some circumstances, you can see the flow. So in order to solve the Stefan problem with the flow, this is a step forward. So in order to solve the flow, you have to solve this complicated equation. We call it Navier-Stokes equation. I'm sure that you hear about it in fluid mechanics. And Navier-Stokes equation is a combination between mass balance equations or continuity equations and the momentum equations for fluid. In the momentum equations for fluid, on the right-hand side, you have forces. Forces are pressure and the body forces. Body forces comes from the differences in the density or whatever. And you have viscous forces. Now we are mostly interested how that flow influences the position and the shape of the solid-liquid interface. What's happened then? And what we can do about solid phase, we are also say, okay, this is something that works with the liquid. What are we going to do with the solid? In solid, we know that V equal is 0. You will see later that there are the cases where the solid is not equal 0. Solid velocity is not equal 0. So, main idea, and you can find it in most of the books related with the porous media, is to introduce this so-called Darcy equation. Darcy equation is something that works in this diffusive interface. And in diffusive interface, we can say this is a porous media. That means the combination between solid and liquid particles. And in that porous media, instead of that complicated equation, we can have this equation. And say I can calculate V if I know this constant. This is a porosity constant. And if I know the pressure field. So now we are complicating again because we get far away from the two equations, right? We introduce only one enthalpy equations for the solid and liquid. And now, can we combine those two to put it in one single equation and to switch it between solid and liquid smoothly? And, of course, we can do that. How? I put this Darcy term. If you put this Darcy term as a force in a momentum equation, then we have a case as follows. If the G is equal 1, G is a liquid fraction. When G is equal 1, this is infinity. 1 above the infinity is a 0, and this term is disappearing for the liquid phase. You can find it in the book of porous media, this equation. In the solid phase, G is equal 0. That means K is equal K0. And because this constant is very small, it's 10 on the minus 10 or 10 on the minus 11. There is a theory how you can calculate it. 10 on the minus 10. That means 10 on the minus 10 on that side means that only those two parts of these equations exist. So, introducing K on such a way, we can see that we can easily switch between liquid and solid. We have only one equation, exactly as for heat. Okay. Fully enthalpy model. Now we can say, okay, we need to know the flow. We have a flow equations. This is a modified Navier-Stokes equation because we introduced the Darcy law in the momentum equations. We have an energy or enthalpy equation, which is combined with those two. And if you are able to solve these equations, you can see what's going on with the solid-liquid interface. Also, I'd like to emphasize that original enthalpy equation that I showed you in the beginning, which was only diffusion equation, now is expanded with the disconvective term. And note that in this convective term, we assume that solid doesn't move. When solid moves, this term does not look like this. It's quite different. So if you type on Google enthalpy porosity model, you probably will see these sets of equations. And you can use some numerical technique to solve it. We are preferring control volume technique because it's very natural and close to the physics of the problem. And I can show you some results later. Demonstration of how the enthalpy porosity model works, you can find in the paper for melting of a pure gallium from 1988, original paper of Brandt, when they try to see what's going on when you have two insulated walls and two walls between the cold and heated wall, and then you have a melting of gallium. And you can see that solidification front looks like this. In the absence of movement, if you assume the absence of movement, you will have a flat line which is moving from the left to the right. Because of flow, you have a deviation of solid-liquid front. That this model works. This is a comparison. We are aware, if you look at the comparison between experiments and the model, and you can see the very good matching. And this is a classics. If you want to examine the solidification problems, you can use this as a benchmark, for instance. Now, I'd like to go through a little bit. This is everything what I show you until now. It was related with a pure substance. The only what you see was the flow equations and the energy equation. This is the simplest case. But when you introduce the more complex systems, like two-phase systems, and the typical examples of two-phase systems are different mixtures, like metal alloys, or some solutes of whatever chemicals is, then you will have there is a one undesirable phenomena that we call it macro-segregation. So in the pure systems, you have this situation because the G changes suddenly, and we have a diffusive interface to overcome the problem. But in the metal alloys, there is a real differences between liquid and solid temperature. How we know that? If you know metal alloys and mixtures, has a so-called phase diagram. That phase diagram shows you what is the liquid and the solid temperature regarding the concentration that you impose in the system. So if you have a concentration of, I don't know, whatever, sugar, let's say, you will have these differences. And these differences, you see, it's quite different comparing this parameter. This parameter is a composition or concentration of solute in the main element. So pure examples such a system are alloys. Now, because of this, because of C, we need another equation, another transport equation. And that equation is very similar to the heat equation, you see. It's almost the same as a heat equation. Now, instead of H, we have a concentration. Convective term has a C liquid, and I can also tell you that this is different if you assume that solid doesn't move or move. And the solid particles can be in a form that they are not moving, or if they are moving. So, if you want to examine the system, which is multi-component, you need to have an additional equation. And this is a complete solidification model. Flow model is the same. Only changes is in G. And G is forces, body forces, and usually in the fluids it's because of thermal or solutal contraction of liquid. So if the liquid became cooler or hot, and so the differences can cause the buoyancy forces. We are using Vusanovic approximation. Or if the liquid became more or rich with solute, also can cause the changes in the density. Now, beside the enthalpy equations, you have a compositional equations. If you are able to solve this, then you can calculate the macro-segregation field. So what else you need? I told you before that in order to calculate this, you need to know G. G is a liquid fraction. So you need a more comprehensive constitutive model. And constitutive model for alloys is usually this phase diagram. And these phase diagrams give you some information about slopes of the liquid line, solid line, about partitioning, how much is the concentration of solid is less than the concentration of liquid, and so on. So we use this model. As you can see, the H and C are input parameters. And from these equations, we calculate the temperature, G, CS, and CL. What are the origins for macro-segregation? If you look at the system, let's say this is a cavity which is where we're extracting the heat from the left side, for instance, and everything else is insulated. And then we have a formation of solid, and then we have a mushy region, which can be quite wide. And then we have a liquid phase. If you look deep into the mushy region, you can see this partitioning. So when the solidification starts, solid which is formed is poor with the solute. And that solute has to go somewhere. And they stay in liquid. And because of that, liquid became enriched. And this enriched liquid is advected by the flow at some place in the casting. And then you have a decomposition. You have zones with the positive segregation and zone with negative segregation. This is a very undesirable effect in the metal industry. In the metal industry, they want to have anything uniform as much as possible. And they are very interested for such a kind of phenomenon. We call it macro-segregation. So I will show you some example. This is an example of our calculations that we made and published in 2013 in Material Science Forum, I think. Yeah. And this is an example of aluminum 4.5 copper alloy. This is an alloy that is used in aircraft industry. This is aircraft industry, I think 70-20 or something like that. And this cavity is cooled with a constant heat transfer coefficient. And look at you can see on the right side the picture of the macro-segregation. That color shows you the blue is a negative zone, and the green one is a positive zone of segregation. And despite that, you have those significant channels. There is a lot of discussions about them. Are they artificial or really physical meaning, and so on and so on. This is something which is related with the problem of grid convergence. Now we observed that the results, it's very difficult to get a grid convergence. And we do the research with, this is a cavity which is only 76 by 76 millimeters. And we impose the high grids, 80 by 80 up to the 150 by 150. And we couldn't get, it was surprising that we couldn't reach grid convergence. It's very difficult. And then it's very time consuming for calculations. And then we try to change domain, and we cut domain on half. Instead of 76, we use the 40 by 40. And then we need to close, you see, 150 by 150 give us a dimension of the control volumes almost quarter of millimeter. It's 260 microns times 260 microns. And then we approach into the case when our physics doesn't work anymore, because everything what we use in equations is based on continuum. So when you go deeper, this is some metallurgical details, you can't go so deep. So with the small domain, we achieve the grid convergence a little bit. This is the result. We have a sharpening of these results. I can show you, if someone is interested, I can send you a paper to read about that. So I will close with our next challenge. Our next challenge is a solid movement. As I told you, solid, which is forming on the solid-liquid interface, can be rigid, and we assume that Vs is equal 0, and can be formed as a particles in liquid. We call it undercooled liquid. In undercooled liquid, you can have some spots of making a solid phase, and that solid phase is not attached to the solid liquid surface. And then you have to take it into account in your calculations. How? You have to separate the enthalpy, because in energy equations now you will have a movement of the solid phase and the liquid phase, and those velocity shouldn't be equal. We have some extreme cases when we say, okay, it's equal or equals 0. This is the two extreme cases. And I can show you, and it's very known from literature, that solid movement has a dramatic influence on the size and the shape of the Maschy zone, the size of the shape of the Maschy zone, and also on the solid-liquid interface, and has a dramatic change, dramatic influence on the macro-segregation, hopefully positive. Not so everything is negative, but hopefully positive. So the people in the metal industry using a refinement to put in the alloy in order to induce such a kind of solidifications. Not to be rigid, but prefer to be equiaxed. This is some preliminary results. We imposed I agree with Van about some physical model. We used this rectangular channel, and we imposed the flow from the left side. We imposed the cooling from the top, and we say, okay, the pressure on the right side is constant. And on the bottom, we have an insulated wall. And then we run the two extreme cases. First one, we say US is equal 0. And another extreme case is we say US is equal U is equal UL. And here you can see the difference. This white line shows the position of the Maschy zone, beginning of the Maschy zone. So on the red color is a purely liquid, blue color is a Maschy region. And you can see the huge difference between when you applied this case or this case. What is the real situation? We don't know. We have to introduce another parameter. We call it GS-pack. So GS-pack is a parameter of solid fraction where free-moving solid stops to flow. So this is another parameter, another complexity. For the beginning, we want to understand the problems, and we will stick with only heat equation. We will not try to introduce the concentration equations as yet, because we want to understand the phenomena and what's going on and so on. So maybe on the next time I will have something more to show you, and I'd like to thank you for your attention, and I will be more than glad to answer on your questions.
Thanks, Igor. A very nice and concise overview of solidification research and some of the kind of current issues that people in that field are facing. Do you have any questions, anyone? So I'm going to start with one. One thing you didn't explain was, if you go back to the last slide you showed up, could you just tell the audience why there is a difference between those? What's the main thing that's driving the difference between those two results?
Yeah. On right side, there is no, we impose the potential flow. And the potential flow, we establish the parameter of K, which drives the flow. And we say the K is equal 1. So in the right side, you have you have an easy movement of solid. So the solid is, the channel is not stacked on the right side.
What about the advection argument that we looked at?
Advection argument, yeah. We are, there's the net change of the latent heat here is 0. Here is 0. He is not 0. He is not 0. So we can go deep into equations. So net exchange of latent heat on the left side is not 0. So solid-liquid interface or Maschy zone doesn't feel that someone is carrying the latent heat. So I believe that's a question. That's an answer on your question.
Yes.
Thank you for your lecture. I have a question regarding the flow.
Okay.
You have a transition zone where you assume Darcy flow, and then you have outside, you have Navier-Stokes, and then you build an equation which is composite of the two. But I have more fundamental question about the link. You know, you are going from Darcy flow to Navier-Stokes flow. Those are very different equations. I mean, what is the compatibility at the interface? Not even going into the mixed equation.
We're still calculating those equations, but this term became more or less dominant.
No, I understand that. I'm more interested in the physics of what's happening in the transition zone and what's happening outside.
In transition
because
zone,
Navier-Stokes you have no slip, for example,
Yes.
at the wall. But Darcy, you have slip. No, it's
Yes,
fundamental incompatibility between those two equations.
we can control it through the value of the constant K0, and we can impose less or more permeability. This is a rough approximation, and when you are in the mushy region, this term became dominant, and they cancel almost other terms, and then you have a competing with the Darcy term and the pressure gradient. And then this is the base how you calculate the U and V. So it works perfectly in the mushy region and liquid. And also another terms can show up in this flow equations if you allow solid to move. For instance, then you have a, how you call it, solid viscosity terms. And then you have a momentum of the solid which is moving. So it works perfectly.
So it really is the Darcy you're just using as an analogy, not actually solving the Darcy equation in the porous media. So it's not like a classic kind of Brinkman extension type argument that you need to use when you go from the liquid to the... All you're saying is, you're basically trying to say, what I'd like to do is add a momentum sink term to the momentum equations as I go into the mushy region, and the Darcy analogy, or this Carmen-Cassini equation, just allows you to add this momentum sink term.
Do we understand the equation inside the mushy region?
So they're still solving the Navier-Stokes equations in the mushy region.
Yes.
So these equations you solve for the entire domain, but what happens is that sink term just becomes progressively larger as the liquid fraction goes to zero, and eventually it gets to the point where you... Yeah. So it's a numerical fix, but it's not... But you're not actually looking at this, but in the sense the kind of question you were asking, like a kind of Brinkman extension question, that's not really, it could be in play there, but it is a trick. And you could go and look at the two-phase equations and maybe calculate something out from it, but it's a numerical trick that seems to work fairly well, but it is a trick.
It's robust and simple. Vicky?
In the liquid region...
Yes, you need to have it.
Oh, thank you. Is it on? Oh, thank you. In the liquid region, in the nature or in environmental science, most of the time we have a turbulent flow.
Okay.
And you may think of a turbulence as a spectrum of eddies with different size and frequencies. So now the Navier-Stokes equations should be modified to take into account turbulence.
Yes, to use the K epsilon maybe.
Well, okay, let's say that you use some turbulence closure like K epsilon model. But if you consider the diffusive interface between the two phases, you assume certain function, some smooth function that will make a continuity between the two temperatures. But in a turbulent flow, eddies of different frequency and intensity, they will approach that interface and they will move away from the interface. They will continue renewing the diffusive sublayer at the interface. So in that case, that function will change in time. It may change shape, it may change
Width?
width. So how would you take into account this change in the diffusive layer in space and time if you have a turbulent flow?
We didn't have such a case up to now, but this is a good idea because in the real cases of metal alloys, there is a turbulence because when you have a casting, pieces that you cast is a couple of meters, you have a turbulent flow. And that I saw so far is that they take care about turbulence increasing the viscosity, put something with the viscosity. When when you deal with alloys or multi-component systems, then you don't need to have a smooth transition between, like in a pure substance. So the difference between the TL and TS can be tenths of the Celsius. Let's say 60, 40, 50, whatever. So, but it's a good point about pure substances. For instance, for water. Yeah. Thank you.
Again, can I add something to that, sir? People have looked at that. Typically, they use the K-epsilon model, and typically in modeling steel casting processes, the turbulence switches off very, very quickly once you get into the mushy region. So it's just maybe at the very outer fringe. And I think what Igor was saying, that in terms of controlling the thickness in the mushy region, the soluble kind of component is much more relevant on a larger scale. But people have looked at turbulence in these models.
Students?
Any other questions?
You are the same like in my country. Nobody wants to ask.
Okay, let's thank Igor one more time. It's good.
Thank you very much.